a lot to the organizer to give the possibility to present some of these results. And I'm not in your field, let's say, and what Carlos especially asked me is to sort of present, let's say, the new states of matter that people have explored in the concept of cold gases. One of the reasons is essentially that we are now using density functional to study the system. But I would say, and I will try to show you in a quite naive way, and there are many open questions. But what is important for us is that there are many experiments that we can, if one come out with a proper density functional, can try to compare with. So this would be the idea. And obviously, I don't have time to give a full overview of what has been done or people are doing in the concept of cold gases. So I decided to concentrate on maybe two new states of matter that we call either quantum droplets and supersolidity, or if you want, what people refer to Li-Young fluids or liquids. And the reason will come out later, I hope, in the talk. So the talk, as I said, is just to give you an overview. So it's really informal. I have a number of pictures, but I don't want to explain you the pictures, just to show what we can do. Okay, and it will be quite really not with not a lot of equations, because, by the way, we don't have many equations. So this is I hope that most of you most probably is familiar with the concept of condensation, Bose-Einstein condensation, and with the equation of state of a condensate. So I don't know, can I use the blackboard very briefly? So very briefly, if you have Bose gases at very low temperature, essentially all the atoms condense in the ground state, and we have essentially at the temperature and the density of this that are in cold gases, essentially you can consider only S-wave interaction, and therefore the important point for us is that the equation of state of the system, or the chemical potential, is given by the strength of the content interaction times the density of the gas. This is just the basic equation of state. Based on this, people like Gross and Pytajewski derived a dynamical equation for the order parameter psi, which is just, as usual in our system, the order parameter square is the total density of the system. And then using this, we have the so-called Gross-Pytajewski equation, which looks simply like the derivative of time of psi times a sort of GP equation times pi, where this is nonlinear and contains the equation of state. So in particular, aside from the obvious kinetic energy, there will be a term which will look like this. And this is all that we do. And the Gross-Pytajewski equation, by the way, many of you know, unfortunately, Lev Pytajewski passed away just a few weeks ago here in Trento. And by the way, so he was here and still surprised how good is the Gross-Pytajewski. And the Gross-Pytajewski, if you think them of mean field, how good it was to describe more than now 30 years of experimenting cold gases. But now new experiment came. And what happens is the following. Instead of a single component, consider to have two components, gases, okay? So I have component 1 and component 2 at the mean field. Okay, I can use this, but no.
If you press it twice, it will switch to the other.
Okay, thanks. So the mean field energy is just a trivial extension of what I've written here, the chemical potential. So I have the intra-species interaction, Gii, Gjj, and I have the interspecies interaction. So very trivial. But now, if you have more than a single species, what you can check is that if the interspecies interaction, so the interaction between two different species, is smaller or in modulus larger than the sort of square root of the product of the interspecies, you can have a collapse. Simply, the system, the interspecies interaction makes the system collapse. And this was people was expecting. You make this is possible. If you are not familiar with cold gases, let me first of all mention that we are able to change most of the parameters of the system, in particular the interaction strength. And the people were expecting that you see a collapse, so the gas would disappear. What happened essentially was is that it's not disappearing, and the reason because you have to in the energy term, this is the mean field. The next order is the so-called Lewis-Young correction, which is a little bit more complicated, and it's not at all a trivial perturbative calculation, but the new equation of state make the system stable because you have a sort of competition between something which is negative and goes like the density square, and something which is always positive and goes like density to the 5 up. So you have a competition, a small density you can think that can dominate this, but a larger density, the 5 up, could really dominate. And this has been just realized a few years ago in the lab, and people really were able to see that the gas without any trapping was being self-trapped, like a normal droplet. And just to show you, it's not important, just historically, these are the two first experiments in Barcelona and in Florence, where they really saw that the gas, once it's released from usually we have a gas in a trap, and once you release, the gas will really spread everywhere. In this case, the gas was not spreading. So it's really a sort of self-trap due to the fact that you have a competition between n square and then fifth, which is typical of liquid droplet model. Let's say. So once you have a density which is the best density for the equilibrium, and people came out as I saw with a new sort of extension of the original Gross-Pitayevsky equation, and due to the way in which the Lewis-Young appears is just the same order parameter, assuming that the order parameter square is the density, which is not at all obvious as an assumption. So you see, and then there's a competition between a negative term and a positive, and therefore, as I told you, we can play with the number of atoms, with interaction, and we can go with something which is dominated, is still stable, but the stabilizing mechanism is the quantum pressure, so the kinetic energy, to something which is the typical flat top profile, typical of a liquid. So this is really a sort of liquid, and this is really where the competition is between the mean field and Lewis-Young, and at the small density, maybe for you it's not very interesting, but are called Bragg-Soliton, where the competition between a collapse and the quantum pressure, what we call. And here again, just to show that people have seen it, it's not important. So I really see that changing in time, you go from one state to the other. The main problem that we have at the moment is that these droplets are very unstable. So they last not much time, as you see on this time scale, really millisecond. And so one of the ideas is that to study them is that we can also smash them. So we prepare two droplets and smash them. Why this is interesting? Because if you're familiar with liquids, smashing droplets is a way to study the equation of state or how good is the hydrodynamics. And this is what this is. I present this because I was also involved in the project. And this is what happens. As you can imagine, if you make two droplets colliding, they can easily merge and stay there together if they don't have enough kinetic energy. The energy is taken in a completely inelastic collision. Or if you have too many kinetic energy, maybe they just first merge and then start be separated again. Now, the point that, however, can be very different if you have a large number of particles. So if you are in the small density limit or in the large and limit. Let me concentrate, which is more interesting, to the large n, where I told you somehow it's really like a liquid. And I found quite interesting that the simulation, this is the simulation using the density function that I showed you before. So there's a competition between mean field and Lewis-Young. You see that it's quite interesting that the simulation of the Gross-Pitayevsky, standard Gross-Pitayevsky, is very similar to what people found in standard. This is an experiment, it's not a simulation, in a standard liquid droplet many years before. Okay, so one idea is that it seems that it's possible to have a zero temperature liquid behave like a normal liquid. And these people in the experiment really did, depending on the velocity or the incoming velocity, they saw that either they merge and stay together, just breathing because the energy goes in the collective mode of the system, or they first collide and then separate again. So people were able also to write a sort of phase diagram to show that indeed there is a region where really there is an incompressible like regime, that means that we are in the sort of liquid regime. The simulation with the density function is reasonable, but not at all, let's say, is qualitatively reasonable. Saying that is quantitatively reasonable would be too far. Okay, so the conclusion of this very first part is essentially that, okay, we use this energy functional that has been derived with Lee Yang for an homogeneous system. We use for very small droplet, seems to work relatively well. And what is interesting is that we have a clear, an interesting similarity between a completely collisionless system and a fully collisional system. So as I showed you before, between the water droplet and our system, which has no collision because of temperature. So and more recently, people really were able to try to measure, to extract a quantitative agreement with the Lee-Yang equation. And one experiment has been just last year, and they were able to measure the collective modes and compare the collective modes of an experiment with the collective modes given by the density functional. And the agreement was reasonably good. And a more direct measurement of the Lee-Yang has been done in a different system that I would like just very briefly to introduce, just to show you the different system that we have attended. This was the system that I was mentioning. So we have our intraspecies and interspecies interaction. We have, as I told you, if GAB is much larger than GA and GB, we have the droplet. And this comes from the Lee-Yang summing up all the spectrum that in this case of a two-component BC being a superfluid are just two sound modes that has to, you sum up all the energy or the vacuum energy, and resumming you find the Lee-Yang correction. Now, a new tool that we have in the lab is instead to have a mixture where you have an interconversion term between the two, and therefore you reduce the symmetry of the system. Before, you have a symmetry which was broken U1 times U1 symmetry to go to two superfluid. Now, only the total number of particles is preserved, and you have a different system where you have U1 times the two symmetry, and then you want to break U1. Aside from the technical details, you can do again, calculate the Lee-Yang correction, which now depends on this new parameter. And what is interesting is that you can go from, sometimes Lee-Yang is called 2.5 body because it's n to the 5 half. But what is interesting is that playing with omega, you can go for 2.5 body equation of state to a renormalization of the two body, and even it appears a 3-body contact interaction. And this has been recently checked in an experiment, by the way, next door to the recent Nobel Prize, at the Institute of TIC, where they really checked that only considering the renormalization of the two-body interaction, but also the presence of a real effective 3-body interaction, they could explain the data. And you see that our theory is the black line, and the experiment. So it seems to reasonably well work, although still why this should work so well is not clear. Perfect. The last system in the last 5 minutes that I want to present is very similar in some sense. Although the physics looks different, the mechanism of creation of the Lee-Yang fluid is the same. The system is different. So now we have a system where the atoms have a contact interaction, which is this ball, and they have also a dipolar interaction. So having a dipolar interaction, this allows us to have a sort of, it's dipole-dipole, so almost long range, is 1 over R cube. And but this what is important is an anisotropic interaction. Now, as you remember, the dipolar interaction has a larger attractive part than a repulsive. And what happens if you have a gas with only a dipolar interaction, it will collapse. Again, what people were able to use by playing with Pech-Parekasa is possible to go close to the collapse, crossing the collapse, and see what happens. And what happens, quite surprising, is the following. This is a few years ago in the group of Tim and Fau in Stuttgart. He tried to make the collapse, and instead of seeing the collapse, he would say very nice ordered droplets. very long living order droplet. The question is why? Well, again, our idea is as before, is that there is a Li-Yang term which stabilizes, and indeed, what people did was to write a energy function that I will show you later for the system, including Li-Yang. But why is so important? Because droplet we saw already. Well, there are a number of cases. First of all, there are a strong dipolar interaction. So we have droplets that interact to each other via a strong dipolar interaction. But there is something interesting. If you have a superfluid which goes to droplet, is it possible that in between you find a phase which is superfluid plus modulation, which means, but not that the droplets are just isolated droplets. They have a coherence. And if you have a superfluid with a pattern formation that is coherent, this is precisely the ingredient that you expect for a super solid that, as you may know, has been debated in many systems and has been recently seen in condensed matter in spin supersolidity or speculating spin supersolidity, but has never been really seen in helium-4, although for a while seemed to be present. But okay. And by the way, in a few years ago, again, people really realized the supersolid phase, and theoretically, we use this equation. Again, it's a sort of the same, if you want, typical Gross-Pitayski equation that you see in the first part, plus the mean field coming from the dipolar interaction. But what is important that stabilizes everything is this term, which comes from the Li-Yang that is calculated for the dipole-dipole interaction. Now you see here something which is quite interesting. There is 1 minus something 1, and epsilon d just tells you how strong is the dipolar interaction with respect to the contact interaction. Therefore, you can, like a sort of idea, you can have that if epsilon d is larger than 1, the dipole interaction is dominated and you would expect a collapse. If epsilon d is more than 1, you have the standard superfluid. Now you see that there are 5R. This is already quite annoying because it means that if this is large, you can have something which is imaginary. What we do, what the people do, remove the imaginary part, go on and study the system. And here I show you just a few results. We were able to measure and to calculate the collective modes. So the lines are the theory using this energy function. This is the experiment. As you see, here is the superfluid. The experiment is still good. When you start having the strong modulation and the epsilon d larger, well, you get a few points. So, but there are many more experiments. These are also other experiments to measure the collective modes. People now started studying the vortices with the same energy functional. We don't have yet a clear comparison with vortices in theory, but just to mention that it's very interesting because the vortices, and so all the properties for a superfluid can be studied for a supersolid. And the question is whether our energy function is good or not. And as I mentioned, the main problem is that there is an imaginary part that people are removing. And this energy function has been calculated for an homogeneous flat system, and you use for something that is not at all homogeneous. This droplet, due to the dipolar interaction, is extremely small, and the size of the droplet is much more than what you can consider an homogeneous system. But there are many important information, like you know that Leggett, for instance, was the first really trying to understand what is the superfluid density for a supersolid. This in principle can be studied now experimentally or theoretically. What is the meaning of the order parameter? Why we take the order parameter square is the total density. So I let you with this. I hope that I just gave you very fast overview on the new state of matter that we are studying. The method, as I told you, at the moment is trivial. It's a mean field plus Li-Yang calculating the homogeneous and apply a Gross-Pitayski. And we find some qualitative, sometimes quantitative agreement, depending on the state where you are, especially in the superfluid, not clear in the supersolid. There is no mathematical foundation why it should work, while for the Gross-Pitayski there is a mathematical foundation. So, and by the way, these are not the only cases where we are looking for density function. There are low-dimensional gases where mean field does not work. There are the magnetic properties where you are, if you are below the upper critical dimension, you don't expect to work. And there are the cases that you studied already about strong interacting fermion and strong interacting full fermion. So for cold gas, it would be, this is why also Carlos came as Marie Curie to us, would be very good to find a way to determine better or learn more about the density functional and the meaning of density function. So that's all.